Hi, so today we are giving a presentation on the preliminary results of our final project. We used one-hot encoder to pre-process the data. So specifically, we used one-hot encoder to transform the categorical features to a series of binary features so they can be used to apply to the sklearn machine learning models like linear regression and other regression models. This example shows what we did for x0. So basically, we split it into a series of binary features of numerical values, which can be applied later to the regression models.
These are the models we plan to use for our project. The white ones are the ones we have already implemented, and the gray ones are the ones we'll implement in the future. Next. The things we want to estimate is a continuous variable, so we have to use regressor, and some of the models we used are not shown actually in the class. One of them is spot vector regressor. It is very much like the spot vector machine we have learned. However, it is a regressor, a regression with a function that is fx equals x instead of fx equals to sine of wx plus b, which is for the spot vector machine. And that only returns a positive one or negative one. Actually, the spot vector regressor is very much like linear regression. But for the SVR, we can use kernel, and we can add penalty terms, and we can add tolerance epsilon, which is basically that if for certain samples, the error is small, we'll ignore the error and do not penalizing the error. Next. And another model we use is Bayesian ridge. Bayesian ridge is a regression with the idea of Bayes. That is, from the prior distribution, we can estimate the posterior distribution. And ridge is actually an improved version of linear regression. In calculating the parameters for linear regression, we use the least square method. However, in least square method, when xt times t is very close to a singular matrix, we can encounter a problem that a large error might occur when we are calculating the inverse of that. However, by doing ridge will add a regularization in calculating the least square, so we can avoid it. Next.
Here are a list of the testing accuracies that we acquired from the models that we have already implemented. So far, you can see the best model is linear regression, which has R square of almost 0.5. So we used R square as our metric to assess how well the models perform. And R square basically explains the percentage of variance in the original data that is explained by the output of the models. And when we first fitted the linear regression model on the original features, it yielded very unreliable results on the test data. And we had an R square equal to this number, which is not interpretable. And then we fitted the PCA algorithm to the original features. And we found that the number of components needed to capture 95% of variance is 136 features. And with the PCAs, we finally fitted linear regression, which yields a reliable R square of almost 0.5. So the ultimate objectives of our project is to first find the model with the highest accuracy on the test data. We have a benchmark of R square equals to 0.55, which is now the first place on Kaggle. And then we will utilize the best model to find the most important features that impact vehicle inspection time the most. Thank you for your attention.